All right, guys, we are starting our next topic in this unit, and it's all about water and the properties of water. And so before we begin, I want to draw your attention to an underlying theme in a lot of science. And so perhaps you have heard of this or had a conversation in a previous science class. The idea that the structure of something or the shape that something takes on determines its function. And so we see this theme emerge where, because of the way something is organized, or in this case, put together, its structure, it then allows for that particular thing to do something unique. And I think about examples from the baby world. When I had kids, so many toys were structured in a way to make noise, make a certain movement, engage my little babies in something. And so structure, or the shape of something, determines what it can do, is a prevalent theme throughout science. And so we're going to talk about that today by looking at the structure of a water molecule and then noticing that because it is put together a particular way, it then allows for properties of water or functions of water. And so let's start with the structure, right? If the structure determines what the water can do, then let's start with the structure. So you know that water is H2O, right? So it's made of one oxygen atom and two hydrogen atoms bonded together. So here's our oxygen and our two hydrogens. Now, holding the hydrogens to this oxygen are polar covalent bonds. So there are two polar covalent bonds holding a water molecule together. How do we know they're polar covalent? We run it through the same filter that we've been talking about related to bonding. Oxygen and hydrogen are both nonmetals, and so we know nonmetal bonded to nonmetal gives us a covalent bond. And then if we look at their electronegativity values, oxygen and hydrogen have different electronegativity values. So we know that one, in this case oxygen, will hog the electron around itself more frequently, making the oxygen end of the molecule slightly negative and the hydrogen ends of the molecule slightly positive. So that's a polar covalent bond creating a polar molecule. So water is a polar molecule with two poles, one negative pole and one positive, slightly positive pole. So there's our last bullet related to the structure. Because there are polar covalent bonds holding this molecule together, it creates an overall polar molecule. So the structure of water, being a polar molecule, allows for it to do some pretty cool things. So structure, its polarity, determines the functions or the properties of water that we're getting ready to talk about. Remember this kind of funny symbol, this Greek symbol for delta means partial. So the partial positive ends of the water molecule, again, are these hydrogen ends, and the partial negative is the oxygen end. Now, in talking about the structure of a water molecule, we can also talk about hydrogen bonds. So because water is polar and because water has hydrogen bonds, or because water has hydrogen in it, H2O, then we can discuss hydrogen bonds. So hydrogen bonds will form between water molecules and neighboring water molecules. Now we saw in our bonding notes that hydrogen bonds form off of the hydrogen of one water molecule to the neighboring oxygen in the next water molecule. So that only happens because there's hydrogen in the molecule and the hydrogen is slightly positive and will form these attractions to the negative end of another. So it only allows for hydrogen bonding because of its structures. But these hydrogen bonds are the reason that all the functions of water, the properties of water exist, that we're getting ready to continue taking notes over. When it comes to the hydrogen bonds, though, you should know that one water molecule can have a maximum of 4 hydrogen bonds off of it. So if we look at the central water molecule right here, we see that one hydrogen bond off the hydrogen foot, another hydrogen bond off the second hydrogen foot, and then 2 hydrogen bonds off of the oxygen end out to neighboring hydrogen ends of these water molecules. So 2 off of the oxygen and 1 off of each hydrogen give us the 4 maximum H bonds that can come off of any one water molecule. So if we know water is polar, and we know that the polar nature allows for hydrogen bonding, then let's talk about how that structure allows for some unique properties. Now, your notes are set up to talk about 4 emergent properties. So an emergent property is kind of as it sounds, it's something that emerges as a result of, in this case, the structure of water and the collection of hydrogen bonds that can exist between water molecules. Now, there are 4 emergent properties. We're going to talk about 2 of them, and the note section will end, and then we'll have a second note section to finish up the last 2 properties and to talk about pH. So essentially, I'm cutting this notes packet in half, so 2 lecture videos to complete it. So we're going to talk about the first 2 emergent properties here. So the first emergent property is really facilitated by something called adhesion and cohesion. So first, in our notes, we have to know, what are they? And this picture helps us to kind of see what they are. This picture right here is in our notes packet. So this is the idea that water is a, quote, sticky molecule, meaning it can stick to a lot of things. And the reason that it can stick to a lot of things is because, number one, it has a positive and a negative end, so it can attract itself to something that is positively charged by using its negative end, and it can attract itself to something that is negatively charged by using its hydrogen feet, because those are positive, right? Positives and negatives are attracting. But also, water is sticky because of those hydrogen bonds. So if water is sticky, let's talk about, what does it stick to? So cohesion, co as a prefix, is kind of together. So you can think of other words that start with co. If you collaborate, you are working with someone else. If you have in the workforce a colleague, CO, colleague, that's somebody that you work directly with. Cohesion is when water sticks to, or hydrogen bonds to, a neighboring water molecule. So here's cohesion, water to water. Adhesion is when water sticks to anything else. And so here's a water molecule that is stuck to something else, this big green blob representing something other than water. So cohesion is water to water, adhesion is water to something else. Here's another great example of adhesion and cohesion working together, which a lot of times we find this happening. We find water sticking to water, cohesion, and then we find those collective water molecules then sticking to another substance, which is adhesion. So what are adhesion and cohesion? It's the collective property that water is kind of sticky and sticks to a bunch of stuff. If we're talking cohesion, water sticks to neighboring water. If we're talking adhesion, then water sticks to something else. And most times we don't see these operating in isolation. We see them operating together. And so let's talk about what these two properties together can lead to, a couple of natural phenomena. So I'm betting that many of us have seen at some point a bug or a leaf that lands on the surface of the water. And there's nothing magical about that bug. It's that the water has created something called surface tension. And so here's a nice picture of surface tension, sort of illustrated. Look at all these water molecules. So not only do we have water molecules that are attracted to neighboring water molecules, hydrogen bonded to neighbor water molecules, that's called cohesion, but then you also have some adhesion happening. So imagine if this were a lake, you would have the banks of the lake here that these water molecules would attract to. You've got some adhesion happening on the bottom of the bug's foot, where the water is attracted to the bottom of the bug's foot, holding it in place. And so essentially, you have a collective, a whole bunch of water molecules, hydrogen bound to each other, that are creating a surface that the bug can exist on. So as long as the mass of that insect is light enough or is less can be supported by these water molecules, the bug will stay on the surface. But we know that if we took something like a rock and tried to place it on the surface of the water, the mass of that rock is too great. It will break the hydrogen bonds between the water molecules. It will break the surface tension, and the rock will not stay on the surface, but instead will sink to the bottom. Another thing that adhesion and cohesion together create is something called capillary action. And capillary action is when water moves up a skinny tube. So the water molecules here are stuck to each other, but then they are also stuck to the sides of the tube, and they are crawling, pushing, using that sticky adhesion property on the sides of the tube to drive up, 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 up. Now, why is this important? Here's sort of a molecular picture. Water sticking to the sides of the tube and working its way up, pulling the water molecules underneath up with it because one water is stuck to another. So we see both adhesion and cohesion working here. Why is capillary action important? Well, one connection to capillary action is called transpiration. And this is the movement of water from the roots of a plant all the way up to the leaves of a plant, where photosynthesis, PS for shorthand here, where photosynthesis is actually happening. So maybe you learned a little bit about photosynthesis last year, and you learned that really the process of photosynthesis occurs in the leaf because it's nice and open and collecting sunlight. But photosynthesis needs water, and water is absorbed at the base or the roots of a plant. And so we have an issue. We have water that is needed for photosynthesis not in the right place for photosynthesis to occur. So that water has to fight gravity and drive itself up, 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 up the trunk and the stems of the tree, the branches and the stems, until it makes it out onto the leaf. And so that movement, specific in plants, is called transpiration. But really, what transpiration is capillary action, the movement of water through tiny tubes using adhesion and cohesion. Let's look at a second emergent property. And this is the idea of water's density in different phases of or states of matter. So if you think about in most of the matter that we talk about, if you think about solid, liquid, and gas forms of that matter, which one of those states of matter is it most dense? Solid, liquid, or gas? Think about, hoping that you said solid, right? Most things are mostly or most dense in their solid form. And that's because the molecules pack together really, really, really tightly. Well, here's the crazy thing about water. When water turns into its solid form, we call that ice. Well, actually, because of what hydrogen bonds do when the temperatures get really cold and the water freezes and turns into ice, the solid form of water is actually less dense than the liquid form. And so we get this unique phenomena where the solid form of water actually floats on the liquid form. And that is not normal. Okay, I've put an actual picture here of where we might see this. If you get a cup of ice water, you notice that the ice will float in the water. Some of you know or have seen pictures of, or maybe even seen in person, icebergs. So, you know, these big giant hunks of ice are floating in the water in the ocean. That is a weird thing. Most matter is at its most dense in its solid form. And so we have to take a second and think about why. Why does that happen? Well, it's what happens when hydrogen bonds get cold. So when hydrogen bonds get cold, they actually spread out and take up more space and they lock into what is called a crystalline lattice structure. And some of you that have maybe seen pictures of snowflakes under a microscope, you know about this sort of crystallized structure of water molecules in ice when they get really cold and form ice. So just as a snapshot here, look at this is like a blown up picture of what the water molecules in this ice look like. Look at how far apart they are spaced. They are locked into a pretty rigid structure. And because they have taken their molecules and spread them out over more space, the ice becomes less dense. Here is warm water, water molecules that are close to each other. Here's cold water. So think about the density of cold water is pretty high, which is why in a lake or a pond, you actually get the frozen form of ice floating, but then you see warm water and way down at the bottom, you'll see the cold water because it's so dense. Its molecules are packed so tightly together. So, long story short, this is kind of unique that when water in its solid form, ice, freezes, the hydrogen bonds spread out and lock into place and create a molecule that is less dense. And that is very, very important. So, our last slide illustrates this importance. You're going to see this again. Ice is a natural insulator. And so some of you are kind of going, wait a minute, what? Ice is really cold. It is cold, but it has insulatory properties. And so to jog your mind or to maybe attach it to something, think of igloos. Think of homes that are built out of snow and ice. They last for a really long time, and inside there's actually warm air that gets trapped in there, or if somebody brings in a heating device, the warm air will get trapped in there and it will create, even though it's made of ice, it will create a nice insulated home or shelter. So there's our example of an igloo. Now, here's why this is important in nature. Ice forms on the surface of a body of water and it floats, so it stays on the surface. That creates a natural insulator on the surface of this pond in this example, which keeps all of this water underneath liquid, which is great for the organisms that are living in that liquid water. So if you think about if ice formed on the surface and then sank to the bottom, this layer of ice would sink to the bottom, exposing liquid water here, which would freeze again with the wind chills and the temperatures. And that layer would sink to the bottom, exposing liquid water here that would freeze again. And then if ice didn't float, that layer would sink to the bottom. And slowly, slowly, slowly over time, we would have freeze, sink, freeze, sink. And eventually, this body of water would freeze solid, and that would kill aquatic life. And so, what a great thing that ice floats because it offers an insulating property, keeping the liquid water in these bodies of water truly liquid below so that aquatic life can survive. So, two emergent properties that we have seen so far: the sticky nature of water and the density of water, particularly in its solid form, and how it is less dense and therefore floats and provides insulation. All of that, both of those properties, are the result of the structure of water. It's a polar molecule with a positive and negative charge, and it forms hydrogen bonds. So the polarity and the formation of hydrogen bonds allowed for it to be sticky and to stick to itself and other things. And the formation of hydrogen bonds in cold temperatures allowed for the water to actually become less dense and thus float. So we will pause right here on lecture 1.1. We'll come back in another video and we'll talk about the last two emergent properties of water, as well as something called pH.